Good morning, good afternoon, everyone, and welcome to our next talk in the Canvas series. Today, our speaker is Carol Jones, who's a professor at the Western University in London, Ontario. She's also Associate Dean, Faculty of Staff Relations and Infrastructure. So she's very busy at the moment in this hectic time of teaching online and all the turmoil of the last several months. So today she is going to be talking to us on the understanding BE stars, the viscous disk model. So Carol, you can unmute and share your screen. I'll just mention that I'll be monitoring the chat window. So if you have questions during the talk, I can I'll interrupt and let you ask your question.
Okay, hopefully you can hear me.
Yes, we can hear you.
And my slideshow is coming up, so we're good. There
Looks
we
good.
go.
Looks good. Yep.
Excellent. Well, thank you very much, everyone, for coming to this. I hope that I can make your hour very worthwhile. As Dennis mentioned, things have been very hectic for me as the Associate Dean of Faculty Relations and Staff Relations and Infrastructure, with everything from computer, IT, and we're trying to hire a bunch of people for the fall term to kind of alleviate some of the busyness. So it has been one of those crazy summers, and so I was wondering how I was going to get this talk made and ready for you. But I do want to thank you, because it gave me some dedicated time to set aside and put some of my ideas together. This is a new talk. I haven't given it before, and so I hope that it will come together okay in the time that I had to work on it. So basically, I want to talk about BE stars, and I want to talk about the viscous disk model, one of the leading theories that seems to be successful at describing the observations. So I'm going to give you, we have a talk on stars for a change. I've been noting some of your talks over the summer, unfortunately not getting to as many of them as I would have wished. But I think I needed a little introduction about BE stars, so we're all on the same page. I want to give you what I think is a strong motivation for why we should study these systems and what they can tell us about so many other things. I'm going to start off talking a little bit about static disk models, and then I'm going to move into some of the newer things that my group has been working on, dynamic disk models, and give you a little taste of some of the things that we've discovered or found through our research, and make some suggestions about connections to other objects with disks. So I'll give you a summary of those. If we run out of time, I just maybe won't get to all of them. And so then at the very end, if you stay with me, one of our new simulations that we've run and tested, we've got an unusual result. And so I'm hoping that at the end of my talk that maybe someone in the audience can make a suggestion as to what's going on here. Okay, feel free to interrupt me, or maybe Dennis, if you have a question. I mean, I don't mind being interrupted at all. I'm just worried that I won't see hands or chats when I've got my slideshow seems to be taking up most of my screen here. Okay, what are BE stars? Well, this is a funny, I think, a kind of a funny photograph. It's just an overexposure. But this maybe looks like what, if the sun were a BE star, maybe what we might see. Of course, it's not quite the right colors. The BE stars should be a little bit bluer. They're hot, except maybe the equatorial region and the disk region, which should be redder. The disk gives a lot of, has an infrared and radio excess due to free emission, so maybe should look a bit redder. Note that these stars, they rotate really fast. And this photograph that I got from one of my postdocs, Mohammed Gorgeshi, his brother actually took this photo. It even looks like an oblate star in the middle, is what you might expect to see. So basically, BE stars have bomber lines in emission. And the emission comes from the ionization and subsequent recombination in the Balmer series within the disk. So these emission lines basically fill up the stellar absorption lines, and sometimes these emission lines can be quite very large equivalent widths and actually can dwarf other features in the spectrum. So they're rather, especially H alpha, which is one of the more predominant lines. It's formed in a big area and statistically is very probable. So it is one of the more significant lines. These stars are characterized by fast rotation, as I mentioned. They rotate about 70 or 80% of the critical velocity, we think. And I'll add a little bit more. Why do we think? Well, of course, they are strongly gravity darkening, which I alluded to a minute ago when I mentioned the oblate squished shape. And so the equatorial regions are cooler and don't contribute as much to the flux. So there have been some suggestions that the actual velocities of these stars could be systematically underestimated. Of course, critical velocity, just so we're all on the same page, means that if we were rotating at critical velocity, the material at the equator, which has a lower effective gravity because of this squishing, would become unbounded. But we believe, most people think, that we need some other mechanism to help punch that material off the star and into the disk. Their main sequence slightly evolved. Their masses are like a typical B star. If you took away the disk, for the most part, these stars would look like your average run-of-the-mill B-type star, 3 to 15 stellar solar masses, 3 to 8 solar radii, and luminosities maybe 100 to 10,000 times the size of the sun. They're characterized by intrinsic linear polarization, and that's actually one of the, and I'm going to get back to some of these characteristics as the talk progresses. I've got some images and plots, and so I'll keep circling back to these things. But basically, the linear polarization is just actually caused from Thomson scattering with the free electrons in the disk of the from the stellar radiation. It actually has a long history with these stars, because if you can imagine, if you had a star that was surrounded completely by free electrons, the scattering would somehow all cancel out and you wouldn't have any net polarization. That was one of the initial clues that these stars actually were surrounded by a disk. So it's a very important characteristic. And although Thomson scattering, I'm not going to get to this in my talk today, should be wavelength independent, but because of the opacity of the hydrogen disk, and a signature of wavelength dependence is imprinted on the polarization. So polarization is actually a very powerful tool for these stars. As I mentioned, and I'll show you a spectral energy distribution a little later in the talk, they have an infrared and radio continuum excess due to the radiative processes in the disk. You'll notice that there's no signature of dust. There's not that familiar bump in the dust. So they're basically gaseous disks, and the gas is released from the star and flowing outward away from the star, opposite to what we see in our accretion disks. And they're variable on a range of time scales. And you may have guessed that from the classical definition, because the Balmer lines have been observed at some time, and that automatically characterizes a star as a BE star. There's a variety of time scales, from little hours to days, little deviations in the spectra, all the way up to more significant changes over periods of decades. And those are associated with the complete loss or gain, dissipation or gain of the disk. And then there's some intermediate scales as well. And I'm going to show you a plot in a minute of a period of for a particular star. So just hang on to that thought for a second. So I want to give strong motivations. Why would I care about this group of special BE stars that have disks? I will challenge you. The one piece that I hope by the end of my talk that you can take away is that I think that these things are interesting on their own right. I'm passionate about them. We've got a long list of projects, a never-ending list of projects. There's so much we can learn from them, but they are obviously a unique laboratory for studying stellar mass loss and disk physics. And when we look out through the observable universe, there's a lot of different objects with disks. And I think that, and over time, I've kind of observed, and I even see it in my own students from when they start their PhDs and when they finished, over time, people tend to get very expert in their own areas and get very focused in their area of research. But I think that there's a lot that can be learned by looking out and seeing what the similarities, seeing what the differences are between some of these objects with disks. And I think that they can tell us a lot. I also think that there's a lot that we need to learn about massive star evolution and the loss of angular momentum from these very fast spinning stars has a lot of clues for us. Much of what we know about massive star evolution is known from extrapolation from our nearby sun that we know so much about. And so these systems, though, I think can tell us a lot about some key puzzles in astrophysics. Of course, we don't know for sure why the disk forms. We don't know why some stars will form a disk and then lose it, while others will stay constant for decades. And so I hope by the end of the talk that you'll agree that they're interesting and realize that they do have a lot of potential to offer clues and better understand other objects with disks. I think I will apologize for the, this isn't a particularly clear image, but it's one of my favorites, given that the H-alpha emitting line is one of the predominant features of these systems. I thought I would do a disservice to the field if I didn't show you a little bit about how these lines are formed and how much powerful information can be obtained from studying them. So this is the H-alpha emitting region shown in a plot of the relative flux versus the velocity. And you can see where these isovelocity regions, these lines connect the region in the disk that forms part of the star. So for example, the really fast velocity, isovelocity regions of 175 kilometers per second. And yes, these stars rotate very quickly, hundreds of kilometers per second. They come obviously from the innermost part of the disk, and you can see that in the upper right and left panels. And you can see that this is a 45-degree inclination, and we can see these characteristics double peaked. We often call the red side R and the blue side V. And these stars, for some stars, the violet and the red peaks remain fairly constant. But for other stars, these violet to red peaks alternate over time. And that will come up a little bit later in my talk too. But then one of the most significant pieces that I wanted to show you, note that the H-alpha line is optically thick. So the line forms because the strength of the line depends on the projection of the optically thick region and the source function. And note here in the central, there's a central reversal here between the two peaks. And often I've heard people say that's because of disk absorption, and that's not true. It is simply a geometric effect because of the inclination angle and the foreshortening of that optically thick region. Now there is a group of stars in the BE stars called special ones called shell stars, where that central absorption peak actually goes below the continuum and you're seeing it edge on. That then you can have the disk and the disk reabsorption which causes that central absorption. So what facts do we agree on? The disks, the disks are formed from material released from the rapidly rotating star. And right now, the leading contender is a viscous disk model, and it's very similar to the accretion model developed by Pringle, and it was adopted by Lee and Okazaki several decades ago for BE stars. And right now, this particular model has been the most successful at reproducing the observations from these systems. So, viscous disk model. I didn't want to bring up a lot of equations because that's kind of dull. But I thought I'd tell you the key pieces. So, the viscous decretion model, as the accretion model, is developed with some simplifications for the Navier-Stokes equations. We have a thin disk. We have Keplerian rotation, and of course, any model that you develop has to explain all these things. So the Keplerian rotation, that means your kinematics in the disk is dominated by this fast rotation. The outflow speeds are really small, less than near the star, less than the sound speed. So that means that the disk is gravitationally dominated, slow outflow speeds, geometrically very thin, and any model has to be able to explain the periods for the buildup, the dissipation, etc. Viscosity basically facilitates the transport of angular momentum out from the inner disk outwards in the vertical directions, perpendicular to the disk is hydrostatically supported. And just like the accretion theory, we adopt what's known as the eddy viscosity or the turbulent viscosity, where the viscosity is given by this parameter, free parameter alpha, and it will come up a lot in my talk, the sound speed, which of course will depend on temperature as well, and then the disk scale height. So no, alpha is supposed to be expected to fall anywhere between 0 and 1. So that means, though, that the largest eddies have to be equivalent to the scale height, and the velocity is not larger than the sound speed. Otherwise, the solution would become supersonic and shocks would develop, and we do not see these in these systems. Now, I put this little reminder, n equals 3.5. Most of these, a lot of the historical way that we have characterized the density distributions in these systems backs down some of the work by Renz Waters in the 1980s, where he modeled the infrared excess with the ISO satellite and characterized the density structure with a density, usually rho naught, that's the density at the innermost part of the disk, and then the density falls off with some sort of power law. And generally this value of n falls in the region of a range of 2 to 4. Now, if you take the Navier-Stokes equations and do some approximations, and assuming a thin disk and assuming isothermal, you get an n of 3.5. So that you can kind of keep that number in your head as we continue to move along. Okay, so how does the material come unbound for the star? Well, we know that the key ingredient is all these stars rotate fast. Whether they were always born and they were just born in the tail of the distribution and then got sped up somehow, maybe the course of their evolution, they had a crisis, they had too much angular momentum and have to shed some off. Some seem to shed off material and then settle back down, and yet others manage to keep their disk constant and steady over a long period of time. So we do need to know a more precise role of stellar rotation. Binary systems are particularly interesting. You know, is the gravitational torque from that binary system responsible for helping pull that material from the star? And I'm gonna, many of the results that I want to discuss later in my talk are based on some of these binary systems. Magnetic fields. Magnetic fields always comes up as some way to constrain the disk, and maybe it's providing the source of the viscosity. Of course, the downside to that is, and I think some of Greg Wade's group have shown that, you know, there isn't a classical BE star that's had a large scale ordered magnetic field, which kind of makes this claim a little suspect. However, if you do the math, and I've got some results to show near the end of my talk, where we actually calculate based on theoretical calculations that these ordered fields for a BE star, these fields must be less than about 10 Gauss. So that's really consistent with this non-detection. So it is possible that magnetic fields are playing some sort of role. But the question is, why do some stars form a disk, others lose it, and others stay stable? And I've got a few little diagrams of some variability, just so that you can help understand some of the kinematic structure that we can actually get. I showed you the figure from Bjorkman. When you take that kinematic details from the spectral lines and combine it with, say, interferometry, where you have this other spatial information, you really do get a lot of information to study these disks. And then pulsating. Pulsation is also, you can imagine a pulsating star, that pulsation giving material enough energy to be launched into orbit, but at the same time, that pulsation not wrecking the Keplerian rotation of that gravitationally bound disk. And in fact, one of my colleagues that I work with a lot, Alex Cardofi in Brazil, showed me some preliminary work just a week or so ago about some a particular BE star, and it has multiple frequencies of pulsation, and it was really interesting. They can see that whenever you have multiple pulsations, you could see that increase in the V magnitude just right after this, every time that there was this constructive interference. Okay, and I did want to, because a lot of my talk's going to show some spiral structures and some binary systems where these density distributions are tidally bound to the orbiting companion. I wanted just to spend a couple minutes explaining, what these density enhancements have, what they can show, and how we can see them in the spectra. So this is zeta tau. It's actually a binary system, an early B-type star. Now keep in mind, I told you that they rotated at hundreds of kilometers per second. That means nearest the star, the rotation rates are in hours, but yet we've got these precessing density enhancements that show up on these intermediate scales, and in this particular case, around 4 years. And what you can see in the little cartoons is, you can see the violet to red variations in the H-alpha spectral lines as that perturbation is either going towards the observer or away from the observer. And here's another little probe and the power of spectroscopy. This is the same star, but the infrared lines, the hydrogen infrared lines, are formed in a smaller region, in this dotted region, closer to the star. Whereas the H-alpha line that I've focused on a lot in my talk is formed in a much larger region of order 10 stellar radii. So it's representative of that inner to mid range of the disk. But note that in this particular case, so I realize that the H-alpha line is kind of messy. It's got the triple peak, so it's kind of messy here. But note that the one side of the line is stronger in H-alpha compared to in the infrared line, how they're in opposite sync. And you can imagine if you had some sort of spiral where along that observer's line of sight, where that particular line is formed, then you can imagine that you would have this opposite behavior. So that's kind of an interesting probe, so that you can tell so much from these spectral lines and a lot of details within the disk. Unfortunately, not all BE stars work this way. There are some where the violet to red in both the H-alpha and some of the other lines, the infrared lines that are further in, actually go in sync together. They're not working opposite. Okay, so this is a fairly new paper. One of my students, my master's student, Mark Suffix. The star system is Delta SCO. It's an interesting system. This is an example of some of the earlier work. It's not really dynamic. It's taking snapshots at certain times, looking at the density of the disk and seeing what the physical conditions in the disks are. And actually, in the past decade or so, I've spent a lot of time taking observations and looking at snapshots to better understand the disk, the density, the temperature distribution within the disk. So this is I'm going to be showing some models, and these are all observations right on here, except for the red line. The red line is actually showing us this particular star is in a very eccentric orbit. It has it takes 11 years for approximately 11 years for the secondary to orbit, and it comes plunging in and then goes away again. And so we were looking to see whether or not that binary companion, whether it actually influences the disk itself. So this was the idea to look at. There's lots of things happening. It's a very variable star, but we were looking at whether or not this binary companion influenced the disk. So the two periastron positions are right at these dips, and of course the star, the binary companion, is much further away at the top of those loops. So it's interesting, in the top plot you see the H alpha equivalent width, which is just a measure of the strength of the line, and you can see it's quite variable. It's unfortunate that we don't have observations right in the early 2000s, because you can see it goes down from being very small, and actually that's when the star started to form its disk. The emission became, the H alpha emission line started to grow, and it grew substantially by the time the star was at apastron. And note that once that binary companion was in apastron, you see that the disk, it almost looks like the disk dissipates a little bit. And then what's interesting, and then on the you have the V magnitudes, V photometry on the bottom, and it's of course a little bit jiggly, and you see the same sort of behavior where it starts, albeit with some scatter. It grows at apastron. It kind of things settle down, and it kind of looks like the disk is dissipating a little bit. But in the next apastron, or at the next periastron, notice that the V magnitude jumps up even before the closest approach, and then stays really constant. So it looks like this binary has had some influence in both in the building of the disk and maintaining it. So there'll be another close encounter in 2022, and we're very much looking forward to seeing what happens then. So here is some of the models my student for Delta SCO, and maybe we'll just talk about, I talked about this rho naught, which is in the second panel. That is just the density at the surface, right in the innermost part of the disk. And what Mark did was he took a variety, he made hundreds of models with our 3D radiative transfer, non-LTE radiative transfer code called H-Dust, that was developed by my collaborator in Brazil, Alex Cardofi. And we just tried to best fit the H alpha equivalent width and the V magnitudes to see what we could find out about this particular system. And so you note that, and maybe as expected, there are lots of free parameters, but as the V magnitude increases, you can look compare the top panel and the second panel. You see that the rho naught density actually goes up. When the disk, the V magnitude goes down, you see that you don't need as much density in the innermost part of the disk. Similarly, this value of n, note that as n gets bigger, so n is 4, that means the density is falling off faster. So perhaps when that disk first started to build, the density actually did fall off more substantially. And as things leveled out, you've got a value of n that's a little bit flatter and kind of around that 3.5 value that I talked about earlier. So that's one of the ways that we try to probe the disk. We get the density distribution, the temperature distribution, and certainly by having models that are constrained by different observables that are produced in different part of the disk, gives you strong constraints on the physical conditions at a particular time. And then we started to move away from, we started to move into some SPH codes and some dynamical simulations. And this particular plot was produced by my now is my postdoc, Isabel Sear. This shows the simulation early on. We basically start our SPH code. We assume a mass loss rate, and we let this build disk, and we can turn the mass loss off or on. But note, in this particular system, that the second white dot is the binary companion. And note that after a period of time, you see the development of these spiral arms that are actually tidally locked to that orbiting companion. And there's always two. There's always the trailing side and the leading side. So that was Isabel. This was one of her chapters in her thesis. She varied the misalignment. So she looked at both coplanar orbits, when that companion was inclined to the disk equatorial region, and studied different values of the viscosity parameter as well. It's pretty interesting. What you see when you've got this binary companion, you see, of course, the disk is truncated, as you might all guess from the tidal torques. But you also see an interesting phenomena where the density inward of that truncation radius actually accumulates and builds up a bit. It's almost like the material is stopped from flowing out. So that was quite interesting. So we did some studies and analyzed our density distribution. And of course, with these misalignments, we found that there was some warping in the discs, etc. We looked at the scale heights. We found that the scale height by standard definitions matched when we actually calculated them. But in these regions of enhanced density, the scale heights could be greater than what regular definitions would predict. That's important when you're trying to predict an observable. So that was all very interesting. But then in 2020, during that time, Isabel, in collaboration with some collaborators in Brazil, took all these binary files from our SPH code and wrote an interface to pump all of those files into our 3D radiative transfer code called, I mentioned earlier, HDust. So now, not only do we have the ability to look at these features that develop in these orbiting, with these orbiting companions, we can actually at the same time watch the changes in all the observables. And so it's actually quite a powerful tool, and we're really getting some interesting results. And so what we did in 2020 was we went back to, and we used, these simulations do take a long time actually to run, not even on a parallel processor. So we went back and used the same ones that were produced in Isabel's thesis to better, to investigate the winding of these spiral arms. And some people had gone on, another person, Despo Panaglo, had looked at some of the changes in spectral lines. And so we went back and we reanalyzed the winding from these, of these spiral arms. And basically I can give you the overall kind of result is that basically when the companion doesn't interfere much, so when it's further away or maybe it's highly inclined and not interfering as much, you end up with these more tightly wind spirals. The spirals can happily form. But then when you have, for example, if it's coplanar, that spiral's interacting more, you have these spirals that aren't quite as tightly as tightly wound. And so when we were working on this particular paper, we had a few interactions with the referee, and we talked a lot about, you know, how do we interpret this winding and understand it all? Well, then remember at the beginning of the talk, I talked about, you know, looking out to other fields, and, you know, there's a beautiful image in this, in one of the Galaxy books, and it's probably in other ones as well, in Spark and Gallagher. And we tried to interpret these spirals, and basically they form from individual particles or packets. That there's what's called in our SPH code. And these spirals form because you see the individual orbits, we believe, become elliptical. And so owing to these tidal interactions. So you can imagine that the density would build up at apastron where the velocities are a little bit lower. And so that this particular study, we think we understand why these form, and we understand and can interpret the shapes of these spirals. But we've now got another new project because we're actually going to follow and make sure that indeed what's happening in the disk, we're actually going to follow the particles, try and follow particle by particle. It sounds challenging, but certainly will tell us something else and confirm hopefully what we think we understand. In addition to that, we wanted to say, well, what would an interferometer see in these spiral arms? And I've just shown you a representative of the K-band image. So we took our SPH simulations, we piped them through this H-dust radiative code, and we produced an image. And then we had to kind of work backwards from what we usually do. We took our image, we 2D Fourier transformed it, and then we took all these cross sections in the Fourier transformed image, measured from the spatial frequency corresponding to our image plane. And then the result was kind of interesting. Now, we studied mainly the coplanar case in this particular part of the paper and a pole-on view, just for simplicity. And, oops, I'm sorry, I went the wrong way. And here is your visibility squared versus projected baseline. We basically were able to tease out, well, what would be the major axis? The major axis is the blue. You can see the bigger axis is the one that's resolved a little bit more quickly, and the minor axis in the red. And we subsequently fit, and so basically we wanted to figure out what would we need to detect these deviations from circular symmetry, because you can imagine if you've got these spiral structures in your disk and the only thing that your interferometer can measure is the outer extent of the major axis or the minor axis, you can imagine that your result might be skewed if you've got these density enhancements going around. And then we also subsequently fit the Gaussians along these specific directions. We did it every 1 degree. And this became our effective, for the measurements at 90 degrees, became our effective axis ratios. And we found that these axis ratios can vary by as much as 20%. So that's just depending on the orientation of where these spiral arms are. And then as a final note, we calculated, well, what kind of baseline would you need to detect a 10% deviation from circular symmetry? And you can see here, meters, and in K-band it's 200 meters. So well within the capabilities of current long baseline interferometers. So how am I doing for my time? I'm supposed to, I agree, I think, be finished by about 10 to 3. Is that correct, Dennis?
Yeah, you got about 10 minutes left, plus or minus.
Okay. Well, I'll continue on and I'll see how far I can get. This is my postdoc, Mohamed Gourgeshi. He did this not while he was with me, but while he was in Brazil doing his PhD. This particular show, they've modeled the full light curve of a particular early type BE star. Note that in the top panel, you see the light curve and you see the different values. Each color is a different value of alpha. And basically, you can think of the values of alpha, like the higher alphas basically just speed everything up. So an alpha of 1 is when when you want to build that disk up. So you can see that both for this particular star has 4 distinct periods of buildup and dissipation. And you can see that in each case, the buildup requires a higher value of alpha and then a more slower dissipation. One interesting thing, if you can perhaps imagine a ruler on the bottoms of light curves, you can see that if you can imagine the dissipation and drawing a line, you can see that it's not flat, i.e., what he found was that even in the periods of dissipation, the star is still shedding some mass, so it didn't go to zero. And perhaps, and the other one shows the base density changes in the average, the loss of angular momentum. Perhaps I'll just keep moving along here. I never ever showed any polarization, and because it's such a great diagnostic, I wanted to show this is the same star as the previous slide for the fourth cycle, where Mohammed is showing the percent polarization change in the last outburst. And he used that to actually pin down the inclination of the system. Polarization, I mentioned, was a very powerful tool in even for astronomers figuring out that these disks were thin. But because the number of scatterers is greatest near the star, near in the innermost disk, they actually give you a lot of information where all the action is happening. And so they can be a great probe of the disk in the innermost region. Okay, this is another project that I wanted to show. I believe this star is a true gift. I know I'm going to run out of time, but I've got to show you this and tell you one truly really important caution when you're studying these systems that build, dissipate. So this is a early BE star. It's relatively close. We know exactly when it became a BE star, so we know how long it took to build the disk. And in 1989, it started to dissipate. And it actually completely lost its disk, and the H-alpha line went from being an emission line to an absorption line. And this, I think, was a remarkable opportunity to follow the evolution of the disk. Not only do we know exactly how long it took to build up, we know exactly how long it took to dissipate. So here's the promised spectral energy distribution I talked about at the beginning. The upper black line, these are different observables from different time periods that are reflective of the diskless phase and the disk phase. The upper black line shows that classic infrared and radio excess that are present in BE stars. And so I wanted to show you that. So he's fit a very nice job of fitting the Z with different observations. Here is a plot of the magnitude in the V magnitude. The middle plot, I want you to focus in on it. It's the H-alpha equivalent width. We started our dissipation at this gray line, and the dotted line is when the star actually goes into absorption. And then again, I've showed you the polarization as well. Interestingly, this wasn't done with the SPH code. This was done with a 1D code where you launch material. It's called single BE. There's plenty of Okazaki developed it. It's interesting. Remember way back in the early part of my talk when I told you about with the simplifications of the Navier-Stokes equations that you would predict that n is equal to 3.5. We wanted to fit that SED, and we couldn't do it. We couldn't let this single BE code build up and get this. We needed a disk density distribution with an n of 2.6, which meant it doesn't fall off quite as rapidly as the isothermal prediction. But of course, our single BE code wouldn't allow us to. We wanted to build the disk and have it sit there and then shut it off and watch it dissipate. We couldn't build the disk up to this n is equal to 2.6. That's interesting because it tells you that there's some physics missing in your model. So then what we did was we actually got the density distribution and fed it into the single BE and then watched it dissipate. Note these colors at different stages are going to pop up on the next slide. And here are the H-alpha spectra corresponding to that spectral energy distribution. And note, we've had a lovely sample of H-alpha spectra. And we were able to do the code was set up to do a complete axisymmetric disk. So even though the observations that are in the darkest line in the figure, they're clearly not symmetric, and we don't expect to match that, but we've done a fairly good job, or Keegan has done a fairly good job of matching up all those lines. Note that the actual dissipation of the H alpha line isn't completely constant. These disks, they actually dissipate from the inside out. So when you shut off the mass loss rate, the stuff in the innermost, it reaccretes the star. Stuff beyond the sonic radius continues to move out. But interesting things happen, because when you suddenly clear out a little hole in the innermost part of the disk, then you can ionize other material that wasn't previously ionized. And note that that's why you see this it's not a steady fall off in the H alpha line. Now, remember, one other point that I want to point out. So initially, Keegan assumed a fairly large disk, which many of us do, because you don't want to truncate the disk before anything and cut off part of your solution. However, when you're going to model this dissipation of the disk, if you turn off the innermost part of the density and you've let this huge big disk build, then as that stuff starts to fall in or dissipate or move away, there could be other material sitting there that can fall in and replace some of that other material. And what he found when he initially did it, he couldn't get the outermost to dissipate quickly enough. And he needed a fairly significant value of alpha. And remember, I said that alpha speeds things up, or speed things up for the higher values of alpha. And he actually, the first time through, modeled it and got an alpha of 0.8. However, realizing that, you know what, we've got to go back and do this again. And so we did a more careful job of getting the outer radius of the disk through H alpha equivalent with V band magnitude and polarization. And we also looked to the literature. A colleague, Robert Clement, had reported a much smaller disk. And there's an equation in one of Kritka's papers that I think it's 2011 or 2015 that predicts the outermost radius that this value agrees with. And so then the simulations were all redone. And the ones that I showed you previously with the fits to the H alpha lines, those are the redone ones. But suddenly the alpha, it doesn't need to be such at the maximum range. We got an alpha of 0.4 and an R outer radius of the disk of 115 stellar radius. So that is a real important point, that you have to be able to, oh, and by the way, sorry, I was in my hurry. I neglected to say this black line shows all the models with the alpha that actually will dissipate at the appropriate 21-year period. So the history of knowing what happened to that object are critical when you want to let something dissipate, when there's other material that can be moved around. How am I doing here for time? I am really running short. There is, I won't go into great details. This is the angular momentum output. And angular momentum output is truly model dependent, but there is some controversy in the literature. And that angular momentum, that rate is really important to nail down for stellar evolutionary models and to understand the evolution of these massive stars. So that's a concept I will skip back. The red star is actually the position of the angular momentum loss for this Mohammed's work that I showed you a few minutes ago. We've been working on another late BE star and looking at these LDOT, that's future work. So I will skip ahead to my summary and I'll show you my one little cartoon that's puzzling, and I will then stop for questions. So I really do believe that these physical conditions from the static models will help us build reliable dynamic models. Got to take the history of the disk into account and these buildup and dissipation events. BE stars seem to have higher values of alpha compared to accretion disk. Why is that? We need to figure that out. I know that there's a paper by Rebecca Martin et al., and they show that for accretion disks, if they're fully ionized, they are in the, maybe 0.2 to 0.4. But as soon as you don't have a fully ionized disk, maybe where the magnetic field is making a difference, they're a factor of 10 smaller. So putting all these pieces together can really help us understand other objects with disks. And I reiterate, I do believe that. And we need models that are tightly constrained to observations. So a little bit of background on why I think. So this is an equal mass binary dissipating over 50 orbital periods, courtesy of my master's student, Mark Suffix. But I'm going to skip on to the one. Remember I told you that they dissipate from the inside out? This is a equal mass binary with the binary orbit inclined by 60 degrees to that orbital plane, and it's dissipating over 30 periods. What you notice is really weird, and I don't know why it's doing this. I told Mark that something was wrong with his simulations. He went away, redid them, and did some other convection effect, and we actually plotted the thing in 3D. But you can see with the binary, and it doesn't do that when the binary companion is coplanar. It empties in a very non-uniform way with a much bigger hole on one side of the star. So that I would be really interested in if somebody has some suggestions of things we could check about that. So I really appreciate you coming. I know everybody's super busy this summer with lots of unexpected work that has to be done, mounting courses and running universities, etc. All these people contributed to some of these, many of the work. Isabel, Mohammed, my postdoc, Keegan Marr, Mark Suffolk. I have an undergrad student that helped with some of this work. Anna High Granada is a previous postdoc, and I didn't get to show her stuff, and she was a postdoc with Aaron Siggett and I. I worked a lot with Alex Cardofi in Brazil and his student Amanda Rubio, and also Chris Teichner from Central Michigan. Anyway, thank you very much for your patience, and I hope that I didn't throw too much at you in too disorganized way that you're able to take away some of the interesting things about BE stars. Thank you.
A lonely clap there, but I'm sure it's echoed by everybody else that's watching. Before we start with questions, I just want to, while I was watching, I did a little Googling and discovered that Gamma Cas was the first BE star discovered in 1866. And in fact, that was the first star who ever observed with emission lines. So it's I thought that was kind of interesting. That it goes way back to Session.
It's the first star that I wrote a paper on as a graduate student.
Not in 1866 though, right?
No, I'm not quite that old. But I started in BE stars, then dabbled in star formation, and came back to this passion that I have for BE stars. But yeah, no, my thesis was all about finding self-consistent temperature distributions for these disks, because I mentioned to you that the H-alpha line is optically thick. So in that innermost regions, it's surprising. My supervisor is deceased now, Mike Marlborough, but I remember when I showed him some of my plots of the temperature, I calculated them by balancing the energy, the input, like the energy due to ionization versus recombination and so on, and balance those rates to come up with a self-consistent temperature. And in the innermost region where it's optically thick, the temperatures are actually much cooler in that near the equatorial region. He was sure that was wrong, but you can look in all kinds of papers now that show that
that is in fact true.
It is in fact true, yes.
So we have a question from Doug Johnstone. Doug, go ahead.
Carol, very nice talk.
Thank you.
You started and you ended by pointing out that BE stars are also a nice laboratory for trying to understand the disk. You're using an alpha disk prescription, which I think is absolutely appropriate, But what's probably hard is to try to decide whether it's alpha that's changing or whether what's really changing is CS and H and the
And
coefficients that we use with the alpha. For
yeah,
those of us who do accretion disks, this is a real mess because we can't get at the physics most of the time, but you
right.
can.
Yes.
So what do you have perhaps to help me with? You at the end pointed out that you had a high alpha, but do you really think it's alpha, or do you think it's the other parameters that are actually changing? And is there a hope that you can actually get to them?
So, I mean, and then one thing that I didn't have time to go, I didn't have, maybe I chose too much to talk about, but I didn't go into details. So the one thing that I'm also really good at knowing is the temperature distribution in these stars. And so we have a really good, that's another advantage that we have in some of your accretion disks, because—
You mean the disk, right? You mean
yeah,
the temperature distribution across the disk for these stars.
yeah, yes,
And the
because of course,
ionization?
sure, and then
Yeah,
that changes everything, right? And,
absolutely.
and in fact, it's pretty hard to even disentangle alpha from T. And in fact,
Yep.
in that figure that I showed you of Keegan's, we actually did, and I'm glad you brought the question up because I didn't have a chance to, where is it? I didn't have a chance, I missed mentioning that. We don't have a way of teasing apart the alpha with some of these others. So we hope that by modeling these other observables that we're really nailing it down. But the T, the temperature, because it directly inversely affects your alpha. And what we did, because we've studied BE star disks for a long time, we're one back of the envelope approximation that's relatively reliable is that the BE star disk is about 60% of the effective temperature of the star itself. And that is what is assumed here. So yes, there is other assumptions because it's hard to disentangle all these free parameters. You're perfectly correct.
No, but I'm relying on you is what I'm saying. I'm putting more pressure on you because we're relying on you to show us, seriously, right?
Right. Well,
I like it. Thank you very much. I appreciate it.
yeah, well, there's a lot to learn. And that's why I think that these disks are really powerful, because the accretion disk, like, and you got a big mess there. You've got so much chemistry, you got dust, you got a lot more. We got these lovely thin disks that are completely gaseous that I'm starting to get a really good solid footing on. And so then when we start to probe those and understand those in the alpha, and all of this stuff is everything I showed is just within this year. We're really starting to get a handle and understanding the alpha. And then I hope I can come to you and say, you know what, this is what we found, and what can that tell you about your accretion disks? Or even watching these particles from the binary systems. And actually one thing I didn't mention too was that, I'm interested in these BE X-ray binary systems, because I think once we really truly understand the disks, we're going to be able to go backwards and understand more of these neutron stars that seem to be that are very numerous around a lot of these BE X-ray binary systems. So yeah, thank you for pointing that out. I do think there's lots of clues, and I think over time, and people get, well, I think too, because the literature, there's a lot more to read. People used to read a lot more broadly, and we tend to focus in. So thank you for asking that, and I appreciate that you twigged my memory, and I now know that I forgot to mention about the temperature. But yes, there is lots of variables, and it is hard to disentangle them. You're right. Thank you.
Thank you.
Any other questions for Carol? I have one. I'm intrigued by the dissipation of the disk. I mean, how often is this observed that a star's disk dissipates?
So well, Chi 66O was a true gift. So it's one of the ones that we actually had a lot of observation. It's bright, it's fairly nearby. So it was fortunately observed over a long time, and we had all those observations. That's one thing that's really limiting. It's an unfortunate that for some stars, we just have, observations that are scattered by different observatories, and it's harder. So roughly about a third of them, you see this buildup and dissipation. The one that I didn't show at the end, this one Dell, it's a late BE star. That one's an interesting one too. It has a disk. It's a shell star. It's edge on. Where is it here? Here's its H alpha spectra. Literally for 80 years, there's a few papers that point out, oh, we think we noticed a little minor variations. This particular star has stayed absolutely constant for 80 years, and it hasn't had this buildup. And so I think that there are different mechanisms. I don't think that this is a uniform group of stars. I think that we'll find in certain types of systems, different mechanisms actually operate. And for example, in the Magellanic Clouds, there's way more BE stars. Without the metals, they tend to be able to spin up much more fast and build that disk. So I think there still is a lot to learn, but yeah, about 1/3 of them have that extreme variability. But we haven't been lucky enough to catch one, that's actually completely formed and dissipated. Because what you see is often the one that I showed for my postdoc Mohammed, where you have, it's got a BE disk, and every now and then it does some, has an outburst or has extra material. And maybe that's, it has excess angular momentum and it has to punch that off, and then it'll settle back down to a more normal state.
This may be off the wall, but it seems like this could be a good monitoring program for the 1.2 meter DAO to just monitor a selection of these stars over time and look for changes in their spectra.
Yeah.
Yeah, we already, Dennis, this is David, we already have Pavel Kubsky does that quite often. He has roughly monthly runs. But yeah, I was going to plug the 1.2 meter because it's for robotic operations, so it's easy to monitor these things. I was looking through the archive while you were listing your various stars, and almost all of the data in the archive. So.
Okay, that's great.
Yeah, it's robotic. You don't have to do anything other than submit.
Okay. And whose work did you mention? I didn't quite catch the name, David.
Pavel Kubsky and Stevenson Yang, they've done some work over the years. Stevenson, not so much lately, but Kubsky observes regularly, and I know some of these stars are on his lists.
Excellent. That's a good suggestion. Thank you.
Okay. There's another question from Doug Guys. Doug, do you want to go ahead and ask it?
I didn't know Doug was here.
Hi, Carol. Thank you. This is a great talk.
Thank you, Doug. I hope you're well.
Very well, thanks. Calling from or joining you from Atlanta. And thanks for the plug for interferometry. I think there's a great future there.
Absolutely.
My question was about the models of forming the spiral arms and about what physical processes might act against spiral arm formation. Particularly, I was wondering how gas pressure, high temperatures, or indeed viscosity might tend to dissipate or stop spiral arm formation, particularly close in where the pressures are higher.
Well, interestingly, in the paper that Isabel did, the higher viscosity actually had the more nice tightly wound arms for the binary system, because you can kind of think of it, when that viscosity is higher, then that companion can't muddle with it as much. But I do think that your question too raises a good point, because we really had to think hard when we were trying to interpret the features of those spiral arms in the paper. Actually, the Sear et al. 2020 is actually in press in monthly notices. But what we're going to do is we're going to go back, and I think if you ask me in a few months, I'll have a better idea. What I really want to see is, I want to follow and track these packets or bunches of particles to really make sure that I understand how they're moving in the disk. I assume it's the same as galactic galaxies, but it would be nice to actually watch them. And of course, I showed the K-band because of that interferometry image that we made, not the H-alpha, because the contrast isn't as great in the H-alpha, even though it's a bigger region, because of course of the optical thickness, you can't really see inside of what's going on there. So I hope that answers your question, Doug. Did we lose?
Silence as a yes.
Oh, good.
Okay, I think I'll bring it to a close here. I want to thank Carol again. It was a very fascinating talk about a very classical subject, but one that has a lot to offer for the other aspects of astronomy where these accretion disks are forming. So thanks everyone for joining, and I hope to see you next week for the next Canvas talk, which is on a little different subject, and it'll be Nayesh Asforti talking from the Perimeter Institute, talking on a new way to measure mass. So I think we're going from a very classical subject to something that is a little more esoteric. But, should be fascinating. Okay, so thanks everyone, and have a good week.
Thanks for listening. I appreciate it.
Thank you, Carol.